Okay, so last time we talked about physics, kind of like the basic fundamentals that we need to know, like ions. I think we talked a bit about charge transfer. And then we started to get into quantum, the quantum world. But now I think like I really want to get into it because, I mean, as I said last time, like in the wellness world and a lot of like the spiritual or pseudoscience online, they love to talk about quantum. And like, I don't mean to say that to discredit it at all, but I just think that there's no grounding in actual hard science. Not that there necessarily always has to be for us to take something seriously. Again, like it's not just Western objective science, but I think it helps a lot to connect the two because at least we're giving ourselves something tangible. Like when we talk about the quantum world, like we don't live in a quantum world, at least on the surface. So you live in a material world. So it's good to connect the two just to give ourselves a sense of grounding, essentially, in what the information we're receiving.
So this is, I agree, it's a very interesting concept, which many people use the term quantum physics for the quantum world very loosely.
Yeah.
I think one way to try to understand what quantum physics is to compare it with what we know or what we call as classical physics.
Okay.
Which what you're referring to as we don't live in a quantum world. Well, yes and no, it's the answer.
At least our conscious experience.
Exactly.
Yeah.
So we live in what we tend to call a classical world, which is an approximation. I mean, let's not go into complexity of approximation of the quantum world. But what classical physics is basically the physics around us.
Okay.
How do we move? How the stars move, how the planets move around the stars, how cars move. So motion, heat transfer at the sort of macroscopic scale. So our sort of macroscopic world is governed by classical physics.
Yeah.
Classical physics is also deterministic.
What does that mean?
So that means that with some equations that we can use in physics, I can predict where the car will be, given that it's moving at, 40 kilometers an hour.
Okay.
So I can.
So it allows you to. It can be determined.
Exactly.
What deterministic is.
Exactly.
Okay.
The position of let's say, an object, the speed of the object, the distance it travels, the time it takes, all sort of the properties governing motion can be deterministically, let's say, measured or.
So it's like when you're in math class, or at least when I was in math class in like middle school or whatever, and it's like, if train A is moving, so that's literally it. Like you figuring out how long it's going to take the train to get there is an example of like deterministic nature of classical physics. Okay.
Exactly.
Yeah.
And this notion of determinism kind of breaks down at the quantum world. So what the quantum world is, or what quantum physics is the physics of the microscopic objects. So not the classical macroscopic objects, but the physics of atoms, particles, elementary particles inside these atoms. And the nature of reality there is inherently probabilistic.
Okay, so just before we get into probabilistic, would you say that it's considered physical?
Depends what you mean by physical.
Like, would you consider atoms physical?
So that's
an actual tangible object. Is an atom considered an object, or is it considered a charge? Not a charge, but like, is it considered a potential? Like, what is it?
So that's a very interesting and deep and difficult question.
Okay, sorry.
Which is basically the debate of all the top physicists in the world.
Okay.
But to give some insights into this question, there's this notion in quantum physics that is called the wave-particle duality.
Okay, yeah, we touched on that a bit last time. We can get into it more.
Yeah. So what the wave-particle duality is that there's a duality between, and this goes to your question about is it physical, between the notion of a particle, and by particle we mean something we can define as a let's say an object dimension, even if it's a point-like particle like an electron.
Okay.
And the notion of a wave. And a wave essentially is a very difficult construct in my opinion, but you can think of as a carrier of energy.
Yeah, last time we compared it to sound.
To sound, exactly. Like sound waves, like water waves.
Yeah.
There is
water is a perfect example.
Water is a perfect example.
Yeah.
You have matter waves too.
Matter waves.
Yes. So, for example, in the wave-particle duality, you get this. And I think this touches upon a point where we sort of discussed, me and you, many times, which we can bring in. That's the Young's double-slit experiment.
Young's double slit experiment. Slits, right? Not slits.
Slit, yes. And that's where this duality comes in.
Okay.
So
do you want to get into that?
we can get into
okay.
Try to explain.
So this is just for context. Like this is the big experiment that kind of, in a sense, I mean, I hate to use the word proved, but gave significant credibility to the idea that like reality is not really as it seems, and like the behavior of certain particles is not like when you observe it, it changes, right?
Yes, it's observer dependent.
Yeah. So this is kind of what brought quantum physics into like the popular world, right? Okay. So yeah, can you explain the experiment?
What you said, Hannah, is exactly true.
Okay.
It's one of the sort of foundational experiments
okay.
which shed light into the nature of reality at the quantum level.
Okay.
And which also shed light on the role of the observer.
Okay.
In determining, what particles or what matter is. And the experiment, I'm simplifying it here. The experiment is you have, let's say, an electron beam. So a beam which shoots electrons, electrons being one of the fundamental particles in nature.
Okay.
Now you put these electrons into two slits.
Okay.
So assuming at the first go you don't observe the electrons move in these slits, you get a wave-like pattern on the screen. If you don't observe them, you get what's called as an interference pattern. So you get actually waves interfering. And
interfering with what?
With themselves. So the electron waves interfering with themselves, and you have a pattern, a wave-like pattern, basically, on the screen.
What do you mean by interfering with themselves? Like they're going along a trajectory, like they're going down the slit, and then they're moving in different directions, up and down. Like, what do you mean?
That's one way to
Or are you talking about one electron or many electrons?
So that's the thing. It's hard to talk about electrons as one and many in this case because they're actually waves. So think of them as actual water waves.
Okay.
Think of a water wave having, let's say, an amplitude x like this.
Okay.
Another water wave having an amplitude x.
Okay.
If they interfere, they'll get a bigger wave.
Oh, so that's them interfering with themselves.
And you get bigger and smaller waves depending on how they interfere.
So when you're talking about like the interference, you're not talking about the actual behavior you're observing in real time, but rather the measurement. The representation of that behavior as a measurement on the screen.
So here's the trick exactly, because if you actually measure them before that, you don't get this pattern.
If you measure them before they go through the slits?
If you measure them while they're going through the slits, if you put the camera on the slits, let's say, you don't get this interference pattern.
Okay.
What you'd get is, let's say you have two slits, you get two piles of electrons.
Okay.
Piling up on both sides of the screen.
Okay.
Which is a paradox here because you didn't change anything. Just measured them.
Yeah.
And they behaved suddenly like
differently.
perfect.
So that's like the experiment in the nutshell, that when you didn't measure them or when you didn't observe them, they behaved in one way.
Exactly.
But then when you did, they behave in another way.
Exactly.
When you say observe, and I think we've talked about this before.
Very difficult question incoming.
Isn't measurement observation?
Yeah, I mean.
So like this is where I get stuck with this thing, because it's like you're getting two different outcomes. One, when you say observe, you're saying people looking at it, or who is the agent of observation?
So very interesting, again, difficult question, which is debated by physicists, philosophers alike.
Okay.
But to simplify the answer, measurement here is something broadly defined.
Okay.
So observing is considered measurement.
But when you say observing in this context, does it mean someone looking at it?
So a machine which measures someone looking at the slits.
Yeah.
Putting a camera, let's say, putting a detector. So all of those are sort of considered broadly under what we call measurement.
Okay.
But then I agree with you. Is measurement equal observation?
Yeah.
That's a difficult question. For the sake of sort of this argument, the answer is sort of loosely yes.
Because I don't really understand when you're saying when you measure them before, they don't do this interference thing. But then when you measure them after, it does.
I see.
So where's the distinction between,
good question.
Like in my head, when you say that, it's like, oh, the measurement is like they're picking up something on a screen, but the observing is like someone's like looking.
Very, very good question. I think here we should make the distinction.
Yeah.
When I say measurement of the outcome, it should be sort of measuring on the screen after they did their thing.
Okay.
Observing, when I use the term observe here, is observing them before they basically go to the screen. So observing them enter the slits, basically.
Oh.
Essentially, yeah.
So the difference is whether you're looking at it before or after.
Yes.
Okay.
So exactly. And it's a very good question. And I used both terms loosely. But to sort of summarize, there's two aspects to it. There's measuring the outcome of going through the slits.
Okay.
And this is the thing that changes.
Okay.
And this is where this wave particle duality also comes in.
Sorry. So whether you're measuring the outcome in both cases.
Yes.
But in one cases, you're observing the electrons before they go through the slits.
Or while they're
going through. So in one sense, you're just looking at it after, like you look away, they're doing their thing, and then later you look at the screen.
Exactly.
In one sense, you watch the whole thing.
Exactly.
And that's where you start to see a difference in how they behave.
Exactly.
Interesting.
It's very spooky.
Yeah.
It's basically one of the foundational constructs in quantum mechanics. It's very difficult to comprehend.
Yeah.
And this is where sort of various interpretations of what quantum mechanics is comes in.
Do you think the electrons feel judged?
That's one interpretation. Yeah.
Yeah.
But yeah, so this is and this goes back to your initial question of, are they physical?
Yeah, so what's the implication here? Like, what did we take from this experiment?
I think what we take from this experiment is, going back to your question, which I think is very difficult to answer, frankly, and that is, are they considered physical? And the answer is yes and no. Yes, there are electrons. Yes, they carry energy. Yes, they sort of are the foundations of atoms. Atoms are made of, a big part of them are made of electrons or electron clouds. But at the same time, they do have this wave-like behavior, which is sort of difficult to our normal constructs of physical things, basically.
Yeah.
And I don't know if you want to go there, but then it becomes even more complex in quantum field theory. So not in quantum mechanics, but quantum field theory. But maybe that's another episode.
Okay, yeah, maybe because I'm still trying to like absorb all of this. Yeah. But obviously, okay, this is a paradox, right? This is a prime example of something being itself and not itself at the same time.
Can you elaborate on this point of like paradox in this context?
Because you're saying that they're both particles and waves, right? So and depending on, maybe perspective is the wrong word, but depending maybe on the context.
Context is the right word.
Their nature changes.
I agree. Context is very important here, and this is sort of what some physicists, even some philosophers, like to coin the term of the observer-dependent reality. So depending on what, who, and when observation happens, the nature of reality changes.
You know, this is really interesting because it's so very closely related to psychology and both like the concept of psychological flexibility and concept of identity in the self in more philosophical or yogic theory, is that the self is context dependent as well. So you're like, we have, especially in our Western culture, we have this idea as like our identity is fixed. Like I'm Hannah, I'm a neuropsychologist, I'm a daughter, and then this is my identity. And we have these labels. A lot of people identify with their profession, for example, and like they get all their validation from their professional development, as an example. But that's also really constricting because you're never just an isolated entity. You're always interacting with the world around you, and the world around you is constantly changing. And who you are, what you bring to a situation is very context dependent. Like, I'm not the same person I am hanging out with my friends as I am in a professional setting, like, or with my family or at a party, like.
So if we have masks that we put in each.
I wouldn't say mass. It's more that we have parts of ourselves that come to the surface based on the demands of the context. So when you take that perspective, you realize that your identity is not a fixed, isolated thing, but it's something that is context dependent.
And would you draw? I mean, that's just the thought. Would you draw parallels with what we know briefly about manifestation, that you manifest different parts of yourself in different contexts, or is that not what this is?
I mean, I think the parts of yourself would manifest in different contexts, but I think when we talk about manifestation, it's more in the sense of like looking to the future and trying to direct your life towards like towards what you really value and towards what you really want. So in a sense, yes, because you could manifest like cultivating a certain part of yourself, building it up, if that's something you want down the line. But I think it's more in the sense of like, rather than thinking of ourselves as like fixed identities, our identity is greater than the sum of our parts. You know, we have all of these different parts, and there's actually like a school of psychology called internal family systems, and it's a very, very, very successful and effective therapeutic approach. And it's very closely related also to like yogic philosophy and theory. And it's that you are a family of different parts. Like you have these different personalities that live inside of you. And you have to learn to relate to them and have relationship with them, because yourself, and there's a distinction actually in yogic philosophy between the self, which is like capital S self, and then small s self, which is like your egoic self. But like your true, the true nature of who you are is infinite. And the more you grow, the more you evolve, you build up these different parts of yourself, you grow as a person, and then you end up with this like collection of different parts, and you're not just one of them, you're all of them and more. You know, you're the glue that holds them together. So you need to know how to relate to them, and each of them has their own, like, especially if you're talking about parts of yourself from your childhood that are like, you know, the bullied part of yourself, the fat little kid who was bullied and who never got the love, you know, that kid still lives inside of you, and it can be triggered in certain situations where you feel like you're not worthy, for example. How do you manage that? You have to learn to relate to this inner child. You have to be able to talk to them. And that's how you really learn to self-soothe and integrate parts of yourself rather than rejecting this fat little kid. You have to love it, you know, so that you give yourself that love. So in that way, I feel like it's kind of similar to what you're saying in a way, because it's the nature of how this thing behaves, the electron, is context dependent, similar to the way that the nature of who a person is context dependent. You know, the nature of how a person behaves is context dependent. And I think that can throw people off a lot, because it kind of gives the implication that like, okay, then who am I? You know, like, is there no continuous sense of self? I don't think people like to think of themselves as that. I don't know what the word is, like fragmented maybe, or not like
Coherent.
Yeah. I think people like certainty. That's maybe what it is. Like, I know I am this, you know, I am a neuropsychologist, I am a physicist, you know, like people like to cling to that certainty in such an uncertain world. But I think it's actually like creates a larger illusion, you know, it buys you more into that illusion.
And
that
it
like
breaks easier, I think.
it breaks easier. Totally. Because that you lose your job, then what?
Quantum mechanics is uncertain, so that's
Yeah, so okay, good, exactly. Let's segue back from my tangent. Uncertainty, right?